Veda, when the presentation starts, you let me know the time, okay?
Yeah. In exactly that time we will start. I'll let you know.
So we'll spend like 40 minutes for the technical presentation, and then
Yeah.
Q&A will be for 20 minutes, right?
Yeah. Okay, we'll start. Priyank, can you start the recording and make it live on YouTube? Once you confirm, I'll start.
Okay, I am starting the recording now.
Okay, perfect. Thank you.
Okay. My voice is clearly.
I will introduce first. Yeah. Good afternoon, everyone. Good afternoon, good morning, good evening, wherever you are, from whichever part of the world. Today here we are for the third webinar as part of the webinar series that IEEE Census Council in association with IEEE has started. And before I go to introducing the speakers, I just want to tell all the registrants that now the grouping for design submissions are done. You all should have received by now the groups that you all belong to. And if you haven't received, please send me an email and I will make the corrections. So if you have any questions regarding that grouping and design submissions, also we'll take it at the end of the webinar. So to start with the webinar, I'll introduce the speaker, Sambuddha Khan. Sambuddha is my colleague in Tyndall. He's a senior scientist in the MEMS group at Tyndall National Institute. He's been in Tyndall for last 4 years, same as me, but he goes way back in our association as colleagues in some fashion. We know each other from past 15 years or more, and we both belong to India. So that's where we started our journey together. He did his PhD from Indian Institute of Science, then went on to do his postdoc at UC Irvine in the US, came back to India and worked for industry, and now he is my colleague in Tyndall. He's an expert and has used the SOI process of the previous MEMSCAP Foundry, now the Science Foundry, extensively during his PhD days and even beyond. So he's the right person to actually explain us more technical details of this process, because this is the design rule and process that we'll be using throughout the training and which will be useful for your design submission next year. So Sambuddha, that's you. And I also have the Science Foundry expert on the technical side, Yusha Wave. He will also be there as a panelist to take questions on anything that is technical and non-technical on the Foundry side at the end of the webinar. So I welcome both of you. And Sambuddha, this is your stage and you can take it forward.
Thank you very much, Veda. And thank you for your introduction. So good morning, good afternoon, good evening to all of you. Welcome to the IEEE Census Council and IEEE sponsored MEMS training program. Today, the talk will be on the overview of SOI process flow of Science Foundry. And as mentioned, I'm Sambuddha Khan and I'm senior scientist in Tyndall National Institute. So this silicon on insulator or SOI standard technology MPW service is offered by Science Corporation. And for more reference or to these design rules, there is the link given here. So this link will take you to the docs that is based on the design rules for MEMS SOI processes from Science Foundry. So before I go in detail, I would like to mention about MPW, what an MPW is. And probably in the last webinar, there was a talk on the MPW services. Uh, I would just take a little time to discuss on this. So MPW stands for multi-project wafer. So it's a multi-user process where there could be multiple designs. They can come on the same wafer on the same mask, and then they can be fabricated together. So silicon on insulator process from Science Corporation is such an MPW process or MPW service. It's a highly standardized process, and the design are based on standard design rules. So that all the designs they follow they go through the same process, same design rules, and then they can be fabricated. The yield for all the designs become same. So and in this particular MPW, anybody can participate, starting from academia to industry. And this is a very cost-effective way to actually fabricate your POC designs, your proof of concepts. It is a quick turnaround because they have a dedicated and defined timeline, and where you can send your designs. They will collate the design together, they receive, and then they fabricate. They send you back the fabricated dies in die form as you want, and it takes more or less 12 to 14 weeks probably. So that's why I said, like, it's good for POC and pre-production designs, and you get a number of dies, like I think 15 dies, or if you want, you can order more, even a handful amount of dies for each participant you can get. So now silicon on insulator. I hope you all understand what a silicon on insulator is. And silicon on insulator is a wafer. And when we are in this particular process, we are using silicon on insulator wafers, and that's why we call it a SOI process, or as we are fabricating MEMS devices, so we'll call it as SOI MEMS process. Now, silicon on insulator has three layers. The wafer has three layers. The top silicon layer is called a device silicon, and then there's a thick handle silicon layer, or we can call it as silicon substrate layer or an handle layer. These two layers are basically sandwiched with a buried oxide layer, which is in this particular process the silicon. Let me take as a pointer. So the silicon here, this is a device silicon layer, which is in blue, light blue, and this is 25 micron thickness, and this is the substrate layer, and this is a buried oxide layer of 2 micron, and the substrate is typically 400 micron thickness, and then the entire stack. When you fabricate devices, there are two more metal layer that comes on this wafer during processing. One is for pad metal, which is like pad metal, which is around zero point 0.5 micron, and then another metal that is called blanket metal, which comes around 650 nanometer, or 0.65 micron. So I'll first go through the process, and after I go through the process, I'll talk about the design rules here. So as mentioned, the SY MEMS process, it starts with an SY layer. As you can see here, it is an SY layer with a bottom thermal oxide, and like first step is actually the SY wafer is doped with phosphosilicate glass for doping the silicon device layer. So this is required to actually doping is required, as you know, to increase its conductivity. Mm, so that's why we do a PSG in the front side. So the resistivity is different. Resistivity is lower here, but the resistivity of the silicon substrate is higher. So that's why this will be able to, it has some electrical conduction properties. And then we have like in the second step, what we do is we remove the PSG, which is for silicon glass, and then we replace it with a photoresist. So this after we do a photoresist spin coating here, what we do here is that we perform photolithography of pad metal mask. So this is the first mask that comes with that. So where we do a lift up process, where there is a metal layer of gold and chromium. Gold is 0.5 micron and 20 nanometer of chromium that is deposited using e-beam evaporation technique, and that creates the pad metal first. So here you see after the lift off process is done, the pad metal is actually deposited wherever you want the pad metal to be. So that metal is deposited, and then we go for the main the most important mask, what we call the SOI mask, which defines your actual device that you are going to fabricate. So we go for another lithography step with the photoresist, and then patterning the photoresist with the mask, and then we go for the etching. And this etching etches the silicon by 25 micron, and using a process called deep reactive ion etching. So this gives you typically a vertical sidewall profile. And here there are many design rules for designing this particular mask. So once the the top silicon or the device silicon that is etched, the next step is to actually remove the leftover photoresist. So what we do is we strip away the leftover photoresist, and then we go to the next process where we actually apply a protective front side layer, which is called polyamide, and we to protect the front side, because now the objective is to actually do processing from the back side to open the back side, and that's why we need to protect the front side. And for which, what we do here is we use a mask called trench mask, and we flip the wafer and start processing from the back side. So in this, we pattern the backside, and then first we actually etch the backside thermal oxide, and then followed by a DRI, as you can see here. So this DRI, and it is almost 400 micron thick. So it's a Bosch process which goes down, deep down here, and the etch stops on the oxide layer. And once the oxide layer, the etch is done, so it opens the complete backside of this. And then what we do, the next step is to actually remove the buried oxide here, whatever is there, which is not allowing this suspended device to be released. So that oxide bridge is actually removed from here, as you can see. Once it is removed, then the process is to actually remove this front side protection layer and the backside leftover resist. So in this step 17 to 18, what they do is they remove the front side and backside PR using like dry etch processes. So once it is done, then the only left is to remove the oxide layers where it is exposed. So what happens here is this is where they use a HA vapor H. So it is a hydrofluoric acid vapor that is used to etch away the oxide, exposed oxide, buried oxide, wherever it is there. So, and that creates some undercut inside the buried oxide as well. Like here, as you can see here, it was etched up to this, but after the HF vapor etch, it etches more, and there is an undercut that happens here, and that's why it goes little inside. And that's why there are certain design rules that will be discussed, that how much it goes inside and how much you need to keep, so that your like unwanted areas don't become like they become suspended. So then So more or less the device is ready here. So only one step which is not there yet, which is called the blanket metal. So for the blanket metal, there is a shadow mask that is designed, and that starts with another wafer. So there is nothing to do with the wafer that were being processed. So here, what is done is silicon wafer is taken, and the silicon wafer is etched from the backside to actually create certain standoffs. So these standoffs are for temporary bonding. You'll see later stage. And so what is done here? Then we do a pattern on using the blanket metal to open certain areas where the through like the wafer will be actually etched through. So this is etched through completely. So here you can see that that also uses DRI to etch the silicon wafer. This is a standard silicon wafer. Once it is done, this is a wafer. Though it looks like this is suspended, but this is not suspended. It's like these are certain opening on the wafer. So the cross section looks like this, but there is connection everywhere. So it's not falling off. So this wafer is taken from here, and then it is bonded using temporary adhesive. It is bonded with the previously processed SY wafer, and then what it does is it opens certain area and like protects certain area for the following step where there is a blanket metal deposition is done. So this is also a metal deposition. So wherever there is no opening, the blanket metal sits on the silicon, but wherever there are openings, that blanket metal goes and sits on the silicon, or if you want pad metal to connect or to bias the handle layer, you can use this process. So these are very useful. This is a very useful process step, which actually gives you more like this can be used for different purposes, but one of them is to like electrically ground or bias the handle wafer. So this is where, and then once this metal is deposited, this shadow mask wafer is actually removed, and then this wafer is all ready and ready for shipment. So it is diced, and then it is the wafers or the chiplets are shipped off to the customers or the users. So this is the process, and as you can see there, these are the few devices. So this particular process can be used for inertial sensors fabrication, like accelerometer, gyros, timing devices. It can be used for micrometers. If you use the blanket metal for the reflecting for reflecting the light, then you can use micrometer. You can use this process for micrometer fabrication. It can be used for fabricating any kind of actuators, also resonators. Here you can see these are some images from Simon Fraser University, and then these are the images of the SY devices from my thesis. My thesis where during my PhD, I have used this process for fabricating accelerometers, and as you can see here, this is the handle layer. This area, there is the backside. It is completely open. This is my silicon device, which is sitting on top. So it's a very nice process to fabricate this kind of devices. So there are a set of guidelines for making the mask layout, and this particular process has evolved through process development stages. So there are many variations that I have seen, but now it is very much optimized. uh, so design rules are critical, and they are to be followed for successful fabrication. And these design rules also defines the capability of individual process steps. So what is the kind of minimum feature that you can minimum or maximum feature sizes that you can design or fabricate successfully, and what are the different rules like layer to layer rules to be followed, and there are different other design rules as well. So as you can see here that design rules define minimum and maximum feature sizes. It says it talks about the overlay. It talks about the minimum spaces for all levels. And there are certain rules. They are called mandatory rules versus there are some certain recommended rules. Recommended rules are for better fabrication. Mandatory rules are to be kind of followed by any means. uh, Minimum line width and spaces are the mandatory rules as far as the run is concerned. Um, and violation of any kind of mandatory rules will result in missing or undersized, oversized, and fused structures. So how these SY MEMS design rules look like? So as I have mentioned that there are mostly mask levels, but one mask is actually divided into two of them. So one is called SY and SY hole. I will show you later what is the difference between SY and SY hole and why a separate mask is there as SY hole. But it's just to create holes of similar sizes on the structure, and I'll show you exactly what it is. But the other four layers, like the matte pad metal, which is the first layer, as you have seen. The pad metal is a mask, and that is definitely is going to be a lithography level as well. So this is pad metal, there's SY hole, there's trench, which is for the backside, and then the blanket metal, which I have discussed in the very last stage. So the pad metal here, the lithography purpose, as I have mentioned, that it defines the geometry of the metal interconnects. So it can be used for metal electrical interconnects, and metal, as I have mentioned, it's for chromium and gold. SY is for structures in silicon. SY holes is holes on the silicon structure. Trench is for the through hole structures from the backside. And the blanket metal is deposited another using the shadow mask that I have discussed. So when the users are designing this particular mask, they need to follow certain rules, and one of the rule is to apply proper mask number or GDS mask number in the mask layout. So if there is any kind of mistake in there, one layer can go to the other layer, and then the fabrication will be completely wrong. So that means if you are defining a layer as a pad metal layer, you need to name the mask or the level in the layout editor software. You have to define that as number 5. So 5, 10, 11, 20, and 30. There are five distinct different numbers for each mask, and they have minimum features. As you can see, there are pad metal minimum feature is 3 micron, 3 micron, maximum is 5,000 micron is the pad metal size. SY, as you can see, SY 10 micron, and then there are certain rules like the rule here is minimum feature is, though it's 2.5 micron for non-orthogonal structures. That means if it is non-orthogonal, the structures are non-orthogonal, either it's vertical or horizontal. If 2.5 micron will be the minimum feature size and space. That means you can create a comb drive with with the width of the comb as 2.5 micron, the gap between that as well 2.5 micron. And if they are non-orthogonal, then you need to provide more. So it has to be at least 3 micron, I would say, for non sorry, it is for my mistake. It for non-orthogonal structures, it has to be it has to be 2.5 micron. And for orthogonal structures, if it is vertical and horizontal, it will be 2 micron. So there are some other like for trench as well. The minimum feature size is 200 micron. Maximum feature is 5,000 microns. Now there is another is blanket metal where the GDS level number is 30. Minimum feature length is 100 micron. Space is 100 micron. Space means between two blanket metal there has to be a space of 100 micron. Here as well, the between two trenches there has to be a gap of 200 micron. And then you can have 5,000. Now I'll discuss this particular part later stage. So the maximum etched area. But here, as you can see, the French and blanket metal, all of them mostly they have a maximum feature size which is 5 millimeter or 5,000 micron. So there are now, as you know now that there are 5 masks, and each mask there are mask to mask as we are fabricating one step after the other. So we have to actually follow certain rules that one level to the other level, how they are aligned, how they can be aligned. So as you can see, like there are 5 of them. That the rule is SY encloses pad metal, SY spaces trench, SY feature size, French, French enclosure silicon structure, etc. So you can see here there are different values, and I'll go here next one to discuss how they are. So you can see if you are going to design this particular device where you want a part which is to be carved on the silicon and a blanket metal sitting here, and then this is your pad metal, this is your silicon structure, and this part which is from the back and opening the entire handle layer from the back, then the here this rule ensures that, and the rule, what is the rule? The rule says SY encloses pad metal. So that means the pad metal and the SY layer, there has to be a gap. They cannot, this pad metal cannot go beyond less than 3 micron, cannot come closer to the edge of the SY. So it has to be within 3 microns. So this has to be 3 micron always, it has to be kept. Similarly, how exactly SY spaces trench? So as you can see here is that the trench and the SY, here this gap has to be 50 micron minimum. Similarly, the other one where it says SY feature size is at least, so here the edge of SY edge. So if you are etching a part in the SY and the edge of the SY, so that has to be, and this is the part which is basically the anchor for the design. That has to be minimum 10 micron. Otherwise, this will this will kind of this will be released during the oxide edge process. That's why it is suggested that you have to, if you there is an anchor that is being designed, it has to be 10 micron and more in length and width. So this is the next one is the blanket metal, how exactly it is aligned. So there is a chance of misalignment, and the maximum misalignment for blanket metal to the silicon inside here, it could be plus minus 35 microns. So therefore, the design has to ensure that if it happens, it doesn't affect your functionality. And the last one is here, the shadow mask alignment to SY. So there, as you can see with SY, the shadow mask can be misaligned by plus minus 40 micron, and therefore you need to design, if you want to have a pad metal, a blanket metal sitting on your SY structure for for micrometers, etc., then you need to ensure that if this misalignment happens by 40 micron or so, your structure doesn't do any it is operational. It doesn't. You have to take that into consideration. Now, die size and usable area. So basically, each chip size in SY MEMS process, is 11.15 millimeter by 11.15 millimeters, but you are like the users are allowed to draw within the area of 9 millimeter by 9 millimeter, which is this entire area. And then as you can see in the green area, which is basically the area for the critical features. So critical features are the minimum features. Now, if an user has something of 2 micron, 3 micron, 10 micron, if these are critical features, they are to be within 8.5 millimeter of area. So it is suggested that all these critical features all the critical feature lies within this 8.5 millimeter by 8.5 millimeter area. And these are few rules like the SY mask layer. Now, when we are etching the silicon from the top side, we have to ensure that we don't etch more than 33% of the silicon. If we so that is one of the rule for designing. So whatever design you put here, you have to ensure that the area being etched out from silicon should not cross more than 33%. Similarly, for the trench mask from the back side, it should not be more than 20 millimeters square, or which is 20% of the chip area. Similarly, for blanket metal mask, blanket metal, the deposition or the opening in the blanket metal mask cannot be more than 20 millimeters square of the entire uh, um, uh, entire chip area. So blanket metal mask means the shadow mask, I mean to say. So here the 20 millimeter square is very important, and it cannot be if the opening or the silicon edge is more than 33 millimeter square or 33% of the chip area, the design will be rejected. So what kind of structures are allowed here? So as you can see here that if you want a metal pattern like this, well, this is good. So if this is your metal pattern, you can get this metal pattern. But if you want a metal pattern like this, you cannot get, because you need like we need to design a blank like a shadow mask, and in the shadow mask we cannot really design a structure like this because this will fall off. So therefore, these donut structures are not allowed. Similarly, from the backside for the trench, you cannot have a donut structure in the trench mask. It has to be completely open. We cannot have something like this from the backside. So therefore no suspended full thickness suspended structures are allowed in the SOI process. Now, if you want here an electrical isolation, you need to you need to design in such a way that the entire silicon is also etched. So to get the electrical isolation, if you remember, I mentioned that there is a PSG, as phosphosilicate glass, in the very first step of the process, where the top silicon is doped, and thereby it makes it conductive, and therefore if you have, let's say, if you design this way, that you think that okay, these are two separate pads, but no, they will be shorted because this is conductive, because this is doped. Therefore, if you want a full isolation, you need to cut the entire silicon. So this is, and then there is another. These are recommended rules. Like if uh, fixed cantilever beams are to be designed, this if there is no corner filleting, these are not good from process yield perspective. There could be huge stress for which it can break. Therefore, corner filleting, etc., is recommended always. Similarly, this is also the dimples are also recommended. Like if you have multiple of them, then having certain small dimple kind of structure will actually ensure that they don't fuse to each other, and thereby increasing the yield of the process. So as you can see, the dimples, this is right, and here I see this is they can stick together in the process steps. Now, once the device is fabricated, so there is an option to actually subdice the 11.15 millimeter by 11.15 millimeter chip. And to do that, either in the mask, either we need to provide dicing lines for laser dicing. So there are two types of dicing possible. One is called the laser subdicing, and maximum the chip can be diced into four pieces, either two or four pieces, or you can get the whole chip. Uh, and this is called a designed in subdicing, where it will not be diced, but it will be fabricated in a way that once you receive the devices, you need to just break the beams in between, and they will you will get dies separated. So once you get it, you will get the entire chip, but the user need to break these beams inside here to actually isolate the four chiplets out of them. So this is one. This is called designed in subdicing, and this is called laser subdicing. And if laser subdicing is chosen, then laser subdicing marks or dicing lane, we call it. That has to be greater than 90 micron. I would say 100 micron would be good. And any structure, this is, say, if there's a backside, um, uh, say the trench mask has to be at least 500 micron away from the backside, from the dicing lines, and the metal has to be at least 100 micron away from the dicing lanes. So these are the mandatory rules for dicing, chip subdicing. So general tips. Layout design must be done on Ledit or Klayout, and we should every user must go through the link given here thoroughly for layout design. The layout must be given must have the layer names, GDS numbers, etc. GDS number corresponding to each layer should be used during submission. If there is a layer without a GDS level number, the layer will be ignored. And design rule check must be performed before submission. So thank you. Before I actually go kind of conclude, I have a small demonstration for you. So I have a mask layout. So can you see this mask layout now?
Yeah, we can.
Yeah. So here you can see this is a mask layout using, and I'm using here Klayout. This is a layout editor software, and this was done way back in, I think, during my PhD time, where you can see there are a couple of designs. So these are some accelerometers, gyroscopes, and some designs are there. So as you can see, I showed this design and how exactly this has been kind of designed. So you can see this is a whole shape. So I'll show you one. So I'll show you all the layers. So you can see the first layer is the metal. This is pad metal. So this is where the pad metal will come. Okay, and as you can see here, the pad metals here, it is pretty small, and but still it is 40 micron. Minimum is 3 micron by 3 micron. So you see here, we can have padmet, and you can use that layer for writing anything, for device numbers. You can use them for electrical pads and etc. As you can see, I have used it for different purposes. So this is the first mask. Then the next mask is the device. So this is the device layer. This is silicon. This is used to etch silicon. Now I'll show you what is SOI and what is SOI hole. So what I wanted is to fabricate is not only this. I wanted to fabricate actually this kind of device. So this was my device. Now you can see SOI hole has only holes, and I wanted to have some holes in my structure, and these are for release. These are release holes, and as you can see, there are holes here. There are small holes here. So all these holes are to be placed in, and here you see I don't have any holes. So if you want holes, you need to put it in the SY hole in that particular mask, and the other mask is SY. So they will be together, they will produce this kind of structure. So if someone wants holes or edge holes or something like that, you should have them there. And then the most important part is, as you can see, this is what is called the trench. So trench is from the back side. So this part will be etched out from the back, as you can see. So whatever here the mask is different. So whatever you are going to etch, it will be dark data. So dark data means wherever it is dark, that part will be basically processed or etched out. So this part will be etched out here. That this part will be etched out. This part will be etched out from the whole chip. So as you can see, I did not want any back edge from here, because I wanted to use these holes for for release. So if you have these holes, and if you keep these holes within 10 micron gap, then what happens during the HA vapor etch, you can actually use the HA vapor etch step to release your silicon without etching from the back. So this is one of the one particular nice feature of this process. And the rest of the designs are, these are not required. So and then there is another one which is called the blanket metal, so which is this one. So as you can see, I'll take out. So these are the blanket metals, and as you see here, the blanket metal is going to sit on the area where this here on the silicon, and also on the, so I wanted it in this way. I wanted the blanket metal to sit on the silicon as well as go on the substrate as well. So it has gone to the substrate, and this is the area. Okay, so as you can see, there is a SY hole here. So that means I have an SY hole. I think I have an SY hole here as well. Yeah. So I have an SY hole, and that means here I will have a hole on the SY. So you can see when I do it together. So this is the area where I will have the blanket metal and the connection to the substrate layer. And this is the layer which you can use it for biasing or grounding the substrate of the device. So that's all I have. So there are 5 of them: 5, 10, 11, 20, and 30. So these are the 5 layers that needed to be designed, and the rest 2 layers was added by the foundry people. And but these are the main 5 layers that needed to be designed. So that's all I have for today. I would be happy to take any question that you may have. I'll just come back to the presentation. So thank you very much to everyone.
Thank you, Sambuddha. Any questions, please put in the chat box and we'll take the questions about this presentation, as well as any other general inquiry to Science Foundry or about your design submissions.
I had one thing to include in regards to the sub-dicing. So we can go further. It's just an extra little fee. We recently had a company that wanted 9 3x3 dies. So,
oh, wow.
Yeah, it was pretty aggressive, and naturally you're just doing a little more picking and handling.
Yeah.
But
yeah,
we can go a little further.
That's the good news.
Great. So looks like everyone has either understood completely what you have said, or they have not understood anything. So there are no questions. Okay, there is one. It says, thanks for can we have the design tool check in a PDF as a backup? Yusha, it was there earlier from MEMSCAP as a PDF document, the design handbook, but now we see it only in your portal as a link.
Yes. I mean, it's definitely floating around on the internet, so we can
But it's
definitely
it could be little different because in the
little dated.
design handbook that was there from MEMSCAP, they have 2 different thicknesses of device layer, but
Right.
now you have only 25. So there are few changes. So if you can make it as a PDF document, it is really helpful for people. Otherwise, they need to always have internet access
Oh,
to
got
see.
you. Okay. I will talk to
I
Karen
can
about
see
it.
there are a couple of questions here.
Yeah, now it's coming up. So it's
Okay. Okay. So the first
how
question is why the use of blanket metal for this metallization step? Is it not possible to use any resist? Yeah, so I can answer it probably. So it is the very last stage where we have already, the devices are already fabricated, and when you have a release structure, you cannot really use any more spin coat you cannot do, and that's why this blanket metal step or the shadow mask process has been introduced. So hopefully I'm answering it correct.
Yeah, just to add on to that, yeah, I mean, there is that technical challenge of doing lithography over that
Yeah,
25
oh
micron step height. So it makes
yeah,
lithography.
that's another thing. Yeah,
Yeah.
yeah,
Also, a lot of people use that blanket metal as a mirror surface. So
yeah,
after we do that deposition, there's no other processing. So you'll have a very pristine surface.
right. Yeah.
so can
We do
we
have
make
an access.
can we make a layout design for final fabrication? Is it our design enough? So what each group does is they submit the mask of their device, and we as a committee will be collating it after doing all the design rule check. So what each group ends up submitting is the mask for one device following these guidelines, which was explained now. So the other one is, can we use Clevin for mask layout? Yes, definitely. Clevin is a good tool. And if you are used to Clevin, please use Clevin to create the GDS.
Yes. How to
And
remove front polyamide? Does polyamide affect DRI performance? No, polyamide is it's a dry edge. It's probably use oxygen plasma to remove it, so it
Okay.
doesn't do anything.
Yeah, because that happens once all the deep RE
Yeah, it's
steps are completed.
completed. Yeah.
Yeah.
okay, so I don't see any other question. Yusha, I
The
have a
question is
question.
just
So how thick is the
how thick
polyamide?
is the polyamide? This
Maybe
is
around,
something, yeah,
sorry. Oh, around like 3 to 4 micron.
yeah, yeah.
Yeah. There's one more. What is the
What's the
maximum
max?
device thickness?
It's only 25 micron. That's minimum and maximum. That's the
Yeah,
only available. 25
that's
micron.
that's actually their constraint. I mean, that's as per their device
Yeah,
wafer that they purchase. They're doing it only on 25 micron device layer
right.
thickness. Earlier they had variation, but now it's just one.
Any use of having a contact to the handle layer at the last? Yes, you can use it for so this handle layer can be used as your support, mechanical support, but you cannot use it for increasing your probe mass or something. That's not possible. But you can use it as support. There is no other use of that, and you can use it for your for as an electrode as well for capacitive devices. You can use it for electrode if you can bias it, and that's why if you want to bias it, you have to use that the blanket metal step to have a metal contact on the handle layer. So you need to open up the silicon from the top side and then have the blanket metal, align it properly, and then the blanket metal is deposited on your handle layer, and then later you can connect the handle layer. You can wire bond that outside and take the connection out and bias it or do whatever you want with that.
Everyone is requested to put the message as a general on so that all of us can see. Some of you are putting only direct messages to me or to Sambhuda, and that doesn't help the general audience.
Yeah,
So
exactly. So is it coming to me only what I'm seeing?
some of them are coming only to you, and some of them are coming only to me. So
Yeah, so hold on. Let me go through the questions that are coming. Can I get a recorded video of this session?
yeah, that I'll answer. All webinars are being recorded and it's available on IEEE Sensors Council YouTube channel. So you can go and see the old webinars, and this also will be immediately available. The next question, thanks for your presentation. Is it possible to send an example of the design in order to know the layers? This is what will be taught to you
Yeah,
by your nodal
yeah,
center person. And there's no point in us giving you any particular design, because it's for you to finally sit and design and fabricate and not just modify anything that's done previously. So if we end up giving you any of these GDS, we know what will happen. You'll only end up modifying those small dimensions and submitting it. And that's not what we want. We want you to sit and design, and your nodal centers and your mentors who are attached to you as a group will help you with that. What advantage do we get SOI over just surface micromachining? So Yusha, you want to take that?
The advantage. I mean, I guess typically you'd have to look at what your application is. I guess that question's kind of open to me. So, like, what are you trying to make? Really, the SOI, I guess you have like planar movement, primarily, but I'm sure you could probably design to get out of
yeah,
plane movement.
right. So it's basically, if I answer it, I would be answering like, is the difference between surface micromachining and bulk micromachining, right? So what SY in SY we are doing bulk micromachining. So there are two different, as Usha has mentioned, that the applications are different. Here we are getting devices that are thicker, and in surface micromachining you don't get thicker, but you have better control in terms of. So there are two different types of micromachining processes, and there are applications are different. So that's how they are.
The next question, I have been assigned to a group with 47 other attendees. It's not 47 other attendees. Your group will basically have 15 to 20, depending on which group you are assigned. Those numbers will come down. It won't be that many numbers because all will not participate in the design submission phase. What you're seeing as 47 is actually 3 or 4 different groups within a mentor. So please see the document carefully. It's one group which does not have 47. Each group can submit only one design, and we'll take that forward towards submission. The next one, the space limit is 2.5 micron. Typically, how much voltage is required for electrostatic driving? Yusha, you want to take that?
I mean, that's definitely design question. I mean, I guess what electrostatic, I could drive voltage, that's all dependent on like how much overlap area you have between your opposite electrodes. I guess 2.5. Yeah, I'm not sure. I mean, definitely you would have to do those calculations yourself.
Yeah.
Yes,
It
exactly.
depends
You have to
on
do those design and simulation.
design and
And
calculation.
when
So
you
basically,
do your
most
design,
importantly, you need to find out the capacitance and then find out the force you can generate with that electrostatic force that you can generate with standard formula. So you need to
there
find
is a
out
pull-in
first.
voltage formula. You
Yeah.
please that and calculate it analytically, but you can also see it when you simulate. And when you submit the simulation results to us, we have given you 2 deadlines for reviews. We will actually be checking your results to make sure that what you are showing as result is appropriate and it will not end up breaking your device. That's exactly the reason why we have asked you to submit those simulation results in advance. Also, one device, if it fails, it can end up becoming a problem for the whole wafer, for the whole die. And so we make sure that every design that is put into a mask follow the design rules, and also the stress levels and the voltage levels need to be maintained.
So there are
Ma'am, I have been
two
mapped to 2 teams. So please send a mail to me. Ritesh has sent to me directly. If anyone has been mapped to 2 groups, please send me an email and I will check that. If anyone is not mapped to any group, also please send me an email. That's what I sent you, an email. Please send an email. I cannot be correcting that, the humanly mistakes I've done when on webinar. So send an email. Where can I find my group? You should have received an email by now. If you haven't received, check your junk. If you have not received there as well, send a mail to me and I will let you know. Is SOG process better for metallization compared to SOI process? Who wants to take that? Sambuddha, you share?
Yeah,
Sure.
so I'm not sure SOG process has been discussed here or not.
No,
Was
we
it
haven't.
discussed? Yeah,
No,
so
no.
it's all about SOI process. Now SOG process is silicon on glass, and this is silicon on insulator. This is on silicon, like it is there is the substrate is glass, here the substrate is silicon. Now metallization, better, bad, it depends on how exactly you are going to design, and so and the application as well. So it's I would not say this is bad or this is better. There are different applications for different processes. So
Yeah.
yeah, so
It depends again on what device and what
what
application your
device?
device.
Yeah, exactly. So can we target out of plane accelerometer in SY?
You can.
This is a very interesting. No, you
Yeah.
cannot. You cannot.
You
Yeah,
can do a pressure sensor, but accelerometer, I don't know. Like I
accelerometer
have
is
done,
not.
yeah, it's not feasible. Not that not that it's not doable as per their design rules, but when you think of probing it, testing it, and finally seeing that the whole wafer is safe, out of plane will be a little tricky in accelerometer, but you could do like a pressure sensor.
Uh, I would say even accelerometer, for out of plane accelerometer, you need to have capacitances, and you cannot really get the differential capacitances in which is required for out of plane accelerometer using this process. So that is the typical limitation for out of plane accelerometer using this SY process, because you don't have you can use the bottom the bottom handle wafer as an electrode, but you don't have the electrode other side, so you will not be able to get the differential capacitance. If you're happy with a single side capacitance change, then you can probably design it, but that will not be linear when you kind of you want to test or characterize. It's not going to give you a very good performance.
Yeah. The next one, I make chips in clean room for our project. We use E-beam for a titanium gold deposition. I get nanostructuring on the chips, which affects the device performance. How can I avoid the nanostructuring which happens on the surface? Any suggestions? Sambuddha?
Uh, EV evaporation and nanostructuring on the chips. This could be something in the deposition parameters or deposition tool that is being used. um, Nanostructuring means we need more details. So this is not the right platform to discuss this
Yeah.
fabrication challenges here.
There
So I
can be
think
many reasons that things go wrong in
yeah.
fabrication and very minute
So it is
looking.
difficult to answer that. There could be anything can happen.
Is there any
What is
other?
there is a direct message to me
Okay.
which says, what is the substrate of doped silicon or just silicon? It's just silicon. Uh, it's not doped. That's why we go for the first step, which is PSG phosphosilicate plus, and we dope the top silicon to make it more conductive. What is the exact role of blanket metal and other wafer is being bonded? Yeah, the role of the blanket metal. Blanket metal can be used for two purposes, as I have mentioned. One is for to have an electrical connection on the substrate layer, because in the pad metal step, your the substrate is not open for deposition. That's why it is a separate step, where if you want electrical connection on the substrate, you can use this particular step to have metal deposited on that. The second is to have a metal or a very highly reflective surfaces. Uh, you can use this gold, because this will be high quality high surface finish, metal deposited reflective surface that you can achieve, which could be used for developing micromirror kind of devices for optical applications.
What is the exact role of blanket minute? That's the last question we have.
Yeah,
Any other questions you have?
Yeah, that's the last question I had.
Okay. Any other questions from the audience? If not, Yusha, I had asked Kara in the last webinar also, if you can tell us the exact date that we need to submit the masks in July for the design run.
Oh, she did not
That
get
will
back.
be, yeah, she didn't come back to me with the date. So if you can let us know the date, that will be very helpful for us to plan.
Okay, yeah, I'll follow up on that. Yes.
Yeah. Okay, so I think that's it.
So I'll stop sharing now.
Yeah, you can. Yeah. So thank you, Sambuddha, and thank you, Yusha, for joining. It was very informative, and I hope the audience liked it. The recording will be on IEEE Sensors Council YouTube channel. You can all view it anytime to get more clarity on this process. It's not easy to understand the first time, but you can keep repeatedly seeing it, and your nodal centers and mentors will also be there to help you understand this design rules. So thank you all for joining, and we'll see for the next webinar. It's on 22nd November. It will be 1 hour later than what we started today because we have a speaker coming from the US and it's early morning for them. And Dr. Geronimo will be joining us for RF applications in industry, and we'll also be joined by Dr. Matthias from Robert Bosch in Germany. So you will see different career aspects and career opportunities and career avenues in MEMS domain in the next webinar on 22nd of November. So see you all then and take care.
Thank you very much. Thank you, everyone.
Thank you.
Thank you.